Hi everyone, I am Dhanya SA, m.tech student, IES College of Engineering. Here we are going to discuss on a topic index properties of soil and classification of soil. In this topic we are going through index properties of soil like particle size and relative density and classification of soil. Here we are mainly focused on IS classification and let's go through some problems. Index properties of soil. Soil index properties are properties which facilitate identification and classification of soils for engineering purposes. Index properties are essential to the computation of engineering properties such as bearing capacity, shear strength, permeability, slope stability, and compressibility properties. While understanding index properties of a soil, we get a rough assessment of the engineering properties without conducting elaborate tests. Main index properties of coarse-grained soil are particle size and relative density. Classification of index properties of soil. Index property of soil is divided into two: soil grain properties and soil aggregate properties. In soil grain properties, it includes specific gravity, shape, and size of soil. While it comes to soil aggregate property, it's subdivided into two: fine aggregate properties and coarse aggregate properties. In fine aggregate properties, it include water content and consistency limit. And in coarse aggregate properties, it includes relative density of soil. Particle size. Particle size analysis is a method of separation of soils into different fractions based on particle size. Particle analysis is done in two stages, that is sieve analysis and it is also known as dry sieve analysis, and second one is sedimentation analysis or hydrometer analysis. It is also known as wet sieve analysis. In sieve analysis, it is meant for coarse grained soils where the particle size is greater than 75 micron, whereas in sedimentation analysis is for fine grained soils where particle size is less than 75 micron. Coarse grained soils can be further subdivided into two: gravel fraction and sand fraction. In gravel fraction, the size is greater, the particle having size greater than 4.75 mm, and in sand fraction, the particle size is between 75 micron to 4.75 mm. A set of coarse sieves used for sieving gravel fraction are 80 mm, 40 mm, 20 mm, 10 mm and 4.75 mm. And a set of fine sieve used for sieving sand fraction are 2 mm, 1 mm, 600 micron, 425 micron, 212 micron, 150 micron and 75 micron. Sieve analysis. Sample is dried at a temperature of 110 degrees Celsius plus or minus 5 degrees Celsius and weighed. The sample is sieved by using a set of IS sieves. The sieves are arranged in such a manner that sieves having higher sieve size placed in the top and lesser sieve size to the bottom, and to the lowermost a pan is placed. The sample is placed on in the top sieve and the set of sieves is kept on a mechanical shaker and the machine is started. Normally 10 minutes of shaking is sufficient for most soils. On completion of sieving, the material on each sieve is weighed. Cumulative weight passing through each sieve is calculated as a percentage of the total sample weight. Fineness modulus is obtained by adding cumulative percentage of aggregates retained on each sieve and dividing the sum by 100. Here we go through some equations used for sieve analysis. Percentage retained on a particular sieve is equal to weight of soil retained on that sieve divided by total weight of soil into 100. Cumulative percentage retained equal to sum of percentage retained on all sieves of larger size and percentage retained on particular sieve. Percentage finer equal to 100 percentage minus cumulative percentage retained. The results of the mechanical analysis are plotted on semi-log plot to get a grain size distribution curve with the percentage finer on y-axis and grain size or particle diameter on x-axis on a logarithmic scale. This curve gives an idea about the type and gradation of the soil. This is the figure shows the particle size distribution curve, and it is obtained by plotting particle size versus percentage finer. From this graph, we can find effective size, uniformity coefficient and coefficient of curvature. And for that, we can find the values of D10, D30 and D60. To finding the value of D30, a line is drawn from percentage finer of 30 percentage. A line is drawn to the curve and corresponding value is taken from the x-axis. And this will give the value of D30. Similarly, we can find the value of D10 and D60. This way, we can find the value of Cu and Cc, where uniformity coefficient Cu equal to D60 by D10 and coefficient of curvature Cc equal to D30 whole square minus divide by D60 into D10. Different types of gradation curve. There are three types: well graded, uniformly graded and gap graded. In well graded, the soil has good representation of grain sizes over a wide range and its gradation curve is smooth. For well graded, the Cc value is between 1 and 3 and Cu is greater than 4 for gravels and greater than 6 for sand. For uniformly graded, it has most of the particles of about the same size and the Cu value is nearly unity. For gap graded, a curve with a hump represents the soil in which some of the intermediate particles are missing. In this figure, we can find different gradation curve, and this is the well graded curve and it is smooth and have a wide range. And this shows the uniformly graded and it's a steep curve. This line shows that this shows gap graded curve, and here we can see the hump and it shows some particle size are missing. Next we go through uses of particle size distribution curve. Particle size distribution curves help for classification of coarse-grained soil. The coefficient of permeability of a coarse-grained soil depends to a large extent on the size of the particles. An approximate value of the coefficient of permeability can be determined from the particle size. From particle size distribution curve, we can know the susceptibility of a soil to frost action. Particle size distribution curve is required for the design of drainage filters. We can find the shear strength of the soil and generally a well-graded compacted sand has high shear strength, and the compressibility of a soil can also be judged from its particle size distribution curve. A uniform soil is more compressible than a well-graded soil. Stokes law. Soil particles finer than 75 micron size cannot be sieved. Particle size distribution of such a soil is determined by sedimentation analysis. The analysis is based on Stokes law, which gives the terminal which of a small sphere setting in a fluid of infinite extent. When a small sphere settles in a fluid, its velocity increases under the action of gravity. But the drag force comes into action and retards the velocity. After an initial adjustment period, steady conditions are attained and the velocity becomes constant. The velocity attained is known as terminal velocity. The expression for terminal velocity can be obtained from the equilibrium of the particle. Sedimentation or hydrometer analysis. A hydrometer is an instrument used for determination of the specific gravity of the liquid. As specific gravity of soil suspension depends on the particle size, hydrometer can be used for the particle size analysis. A special type of hydrometer with a long neck is used. The neck is marked from top to bottom, generally in the range of 0.995 to 1.030. This is the neck portion of the hydrometer, and the neck portion are graduated. Next, we go through the procedure of hydrometer analysis. Suspension of 50 gram soil, 33 gram of sodium hexametaphosphate and 7 gram of sodium carbonate is prepared. It is made up to 1000 ml by adding water. The suspension is mixed thoroughly by covering the top of the jar and doing upside down and back a few times. First reading is taken after half minutes. Readings are taken after 1 to 4 minutes. The hydrometer is then removed from jar and rinsed with the distilled water. Insert the hydrometer. Further readings are then taken after 8, 15, 30 minutes and after 1, 2, 3, 8 and 24 hours. Floated in a comparison cylinder containing distilled water with the dispersing agent added to the same concentration as in the soil suspension. Here the corrections of hydrometer readings. There are 3 corrections: meniscus correction, temperature correction and dispersing agent correction. First we go through meniscus correction. It is denoted by cm, and the meniscus correction is equal to the reading between the top of the meniscus and the level of suspension. As the marking on the stem increases downwards, the correction is positive. Meniscus correction is constant for a hydrometer. Next, temperature correction. It is denoted by Ct. Hydrometers are generally calibrated at 27 degrees Celsius. If temperature is other than 27 degrees Celsius, correction plus or minus Ct is applied to RH, where RH is the observed hydrometer reading. Next, dispersing agent correction CD. Correction due to rise in specific gravity of the suspension on account of the addition of the deflocculating agent, and it is denoted by CD. Next, the corrected hydrometer reading are equal to RH plus Cm plus or minus Ct minus Cd, where RH is the observed hydrometer reading and RH is to be used in the calibration graph to obtain the effective depth H. Next we go through relative density. The relative density is generally used to indicate the in situ denseness or looseness of soil. It is defined by the equation dr equal to Emax minus E divided by Emax minus E minimum into 100, where Emax is the void ratio of the soil in loosest state and E minimum is the void ratio of the soil in densest state and E is the void ratio for in situ. The relative density of a soil gives a more clear idea of the denseness than does the void ratio. Two types of sands having the same void ratio may have entirely different state of denseness and engineering properties. However, if the two sands have the same relative density, they usually behave in identical manner. The relative density of a soil indicates how it would behave under loads. If the deposit is dense, it can take heavy loads with very little settlements. This table shows the relative density and a soil condition. If the relative density is less than 15, the soil condition is very loose, and if the relative density is between 15 to 35, the soil condition is loose, and if the relative density is between 35 and 65, the soil condition is medium, and the relative density is between 65 and 85, the soil condition is dense, and if it is greater than 85, the condition is very dense. Next we go through classification of soils. Principles of classification. General classifications. Generally, soil is classified as cohesionless and cohesive, or coarse-grained and fine-grained are too general and include a wide range of engineering properties. Additional means of categorization are necessary to make the term more meaningful in engineering practice. Several classification systems were evolved by different organizations having a specific purpose as the object. Indian Standard Classification System, IS classification system. It is broadly classified into three divisions: coarse-grained soil, fine-grained soil and highly organic soil and other miscellaneous soil material. In coarse-grained soil, in this soil, 50% or more of the total material by weight is larger than 75 micron IS sieve size. In fine-grained soil, 50% or more of the total material by weight is smaller than 75 micron IS sieve size. In highly organic soil and other miscellaneous soil materials, soils contain large percentage of fibrous organic matter that like peat and particle of decomposed vegetation. Particle size classification. In this classification, soils arranged according to grain sizes. Terms such as gravel, sand, silt and clay are used to indicate grain sizes. These terms are used only as designation of particle sizes. They do not signify naturally occurring soil types. Naturally occurring soils are mixture of particles of different sizes. In this figure, we can see that the soils are classified as clay, silt, sand, gravel, cobble and boulders. If the particle size is less than 0.002 mm, it is termed as clay. And if the particle size is between 0.002 mm and 0.075 mm, it is termed as silt. And the sand is here divided into three, that is fine, medium and coarse. For sand, the size is between 0.075 and 4.75 mm. And the gravel is here divided into two, that is fine and coarse. For gravel, the size is between 4.75 and 80 mm. For cobble, size will be between 80 mm and 300 mm, and for boulders the size will be more than 300 mm. Next we go through some prefix and suffix used in IS classification of soil. Here we can see a group of main soil type, and this is the group of subgroup. The main soil type are gravel, sand, silt, clay, organic and peat. And the prefix used for gravel is G, sand is S, silt is M, clay is C, organic is O and peat is PT. And the soil have some subgroups like well graded, poorly graded, silty and clayey. And the suffix used for well graded is W, poorly graded is P, silty is M and clay is C. And another subgroup is there, and it is based on liquid limit. If the liquid limit is less than 35, the suffix used is L. L is nothing but low plasticity soil. And if the liquid limit is between 35 and 50, the suffix used is I. I is nothing but intermediate plasticity soil. And if the liquid limit is greater than 50, the suffix used is H. H is nothing but highly plasticity soil, high plasticity soil. Here we can see some classification groups here. For example, if the soil is well graded gravel, the symbol used is GW. And next, For example, if the soil is low plasticity clay, the symbol used is Cl. And this figure shows the plasticity chart. This is a liquid limit versus plasticity index. Um, this is the this line shown is A line. The equation for A line is plasticity index equal to 0.73 into liquid limit minus 20. Already we discussed in the previous slide about the range in low plasticity, intermediate plasticity and high plasticity. If we have the value of liquid limit and plasticity index, we can find which type of soil it is. Next we go through some small problems. For a given soil, the maximum void ratio is 0.9 and a minimum void ratio is 0.2. The void ratio of the grain sample is 0.4. Find out the relative density. This is we know the equation for relative density dr equal to E max minus E whole divided by E max minus E minimum into 100. From the question we have the values of E max, E minimum and E, where E max equal to 0.9, E minimum equal to 0.2, E equal to 0.4. By substituting the values we get the relative density as 71.42. This question is from IS classification. Write down the symbols for well-graded sand and low plastic clay. We know that the symbol for well-graded is W and sand is S, where S is prefix and W is suffix. Therefore, the symbol for well-graded sand is SW. And next one is low plastic clay. We know that the symbol for low plastic is L and clay is C. Here L is the here C is the prefix and L is the suffix. Therefore, the symbol of low plastic clay is Cl. Thank you.